Okay, well, it's a great pleasure to welcome Constantin Teleman, who's going to be our second speaker this afternoon. And he tells me it's his first time in Dublin, so we're especially delighted to welcome him to Ireland and Dublin. And today he is going to tell us about group representations and to the topological quantum field theories. Thank you.
Yes. Thank you very much for the invitation. This is my first time in Ireland, and you have gorgeous weather here. It makes me want to move from California. It's been cold and rainy all year so far. So, yes, I actually put a little. First question is the handwriting large enough to read? That's the size, because there's another option, which is this, to rotate, but then it only shows half a page at a time, so there's a trade-off. What's the feeling?
Well, I can read the first one.
The first one is readable from the back as well, or?
I think they can move forward.
Okay. So, that's true. There are lots of seats in the front row. So I did put the summary plan here, but it will disappear, so I don't know how useful it is. I cannot display it on the side. And let me try this format, let's see if it works, of revealing things very slowly. It could be a complete fiasco. So let's see. Yes, okay, kind of works. So I hesitate in putting names here. Let me tell you what this is about. So I think over the past 30 years, there's been a change in the way we look at quantum field theory, because the previous 70 or plus years have been dominated by mathematical side by analysis, because there were difficult analytical questions in constructing quantum mechanics and quantum field theory that had to be addressed. And about 30 so years ago, the advent of topological field theories realized that there were difficult algebraic questions to be addressed that we hadn't thought about before, didn't know how to handle. And to some extent, and those algebraic questions appear even when you're dealing with finite dimensional vector spaces, so analysis isn't an issue, just linear algebra seems to be the issue. And you could say to some extent that we've got a handle on those algebraic problems. Something called the cobordism hypothesis tells us now how to handle fully local topological field theories. I'll remind you, I will not state exactly the cobordism hypothesis, it's a theorem, but I'll remind you of what it says. We can make precise the notion of what it means for a theory to be fully local, meaning reducible to structure assigned to a point or a tiny region of space-time, and know how to reconstruct everything from that. So it gets progressively more complicated with the dimension, but the hierarchy of algebraic structures is now somewhat understood. So I think we're moving on to working out interesting examples from the mathematical side, again, as much as possible trying to avoid analytical difficulties. And one of the large classes, interesting classes of physical theories are the gauge theories. So that's what we're after right now. And the first thing I'd like to remind you of, so I put some names here, but I'm not very secure about the origin, because Moore and Siegel and Maxime would probably tell you that in the case of gauge theory, what I'm about to say now was already somehow known, but it was made precise about 20 years ago, roughly, in a long paper by Moore, Siegel, and based on ideas of Kontsevich. If you like, the slogan is that the representations of a group G, which you could start by thinking as a finite group, but progress to a compact group, is what the category of representation is the category of boundary conditions for two-dimensional pure gauge theory with a group G, the same group. For a while they were called branes, but that may have been just a mathematical misappropriation of a physics terms. I think boundary conditions or boundary theories are better. So there's be a bit of abstract math, but I promise the next page will make it more concrete. So a TQFT is a functor from a category of manifolds, in this case dimension 2. And the category is a 2 category because it has objects, which are points, morphisms between points, or one manifolds connecting them, and 2 morphisms between one manifold, which are surfaces. If you go up higher in dimension, there are multiple layers of things. So you can see that the algebra will get more complicated accordingly, because the structure of the geometry gets more complicated because of the many layers. So a TQFT is a functor from this category to a symmetric monoidal 2 category. 2 is the dimension. And a typical example of the target of the 2 categories, the 2 categories of algebras, the objects are algebras. Morphisms between them are not algebra homomorphisms, that would be too easy, but they're bimodules, and the composition of bimodules is by tensoring. And the next layer of morphisms, 2 morphisms, they call that the intertwiners between bimodules. So actually, the theory of von Neumann algebras has been studied already, so it should be familiar to people who have looked at quantum field and the von Neumann approach to quantum field theory. A variant is, instead of algebras, you can look at linear categories, functors between them, and natural transformations of functors, and you get from the first to the second by taking the modules over a given an algebra, you take a category of modules over it, and that will give you a map. And the very informative example, which is the first example you can work out completely, is finite gauge theory. And in this case, let's start from the top. To a closed surface, you assign a number, and that number is just a count of G bundles. When the group is finite, there are finally many G bundles. They have automorphisms, so weigh them a bit, and that's a toy version of your path integral. So instead of integrating over over connections and bundles, you just count necessarily flat bundles. To a circle.
One request: can you make it a bit larger? The ones it was.
That's what I was. That's the only. These are the only 2 options, and then you get to see half a page. See, that was the dilemma. Is that all right, or?
It seems a bit more readable than the previous ones.
So. I don't know whether there's something showing up a black stripe on the.
I think somebody was
Right, because it's not showing up on my screen, but well, let's try to.
This one.
Anyway, so let's start from the top. So to closed surface, as I said, you assign numbers as a partition function, and that's the path integral, quote unquote, which counts G bundles. To a circle, you have to assign a Hilbert space of states, and in this case, that's a space of functions on G bundles over the circle. And the G bundles on a circle are characterized by the monodromy, which is defined up to conjugation. So these are really class functions on the group. That's a space of states. And to a point, as I said, you should assign a category or an algebra, and the category would be that of representations of G. The algebra, if you like, would be the group ring. Modules over the group ring are the same as representation of the group. If you want to make it look a little more like a path integral, you can use a 2 co-cycle on the group, which gives a projective, an extension by C star. And this 2 co-cycle allows you to put complex weights on G bundles. So instead of counting them as 1 or 1 over the order of automorphism, you can put a complex, non-zero complex number computed from this co-cycle. And instead of the space of functions on conjugacy classes, the same co-cycle defines a line bundle on G mod G, it's a central extension line bundle, so you take sections of that. And instead of ordinary representations, you take projective representations. And the algebra in this case is a bit more complicated because of the numbers, but formally it works in the same way. And this, you want to think of it as the exponentiate action, the thing you would write in the path integral. It begins to look a little more like a path integral. Yes?
What is the G bundle over S1?
G bundle over S1. So G is a finite group to begin with. In this, it's easier to explain for a finite group. And the G bundle on S1 is simply classified by its monodromy, which is a group element, but modding out by conjugation by G. So I could have said class functions, but then the pattern would be a bit less obvious. You're always looking at G bundles over the point. And in the first case, you're just counting them. In the second case, you're kind of counting them in the vector space world. You're assigning a line to each of them and taking the direct sum of lines. And in the third case, I will try not to explain that. You're counting them in a categorical sense.
these are all flat bundles.
These are flat, but when G is finite, they have to be flat. If G is a Lie group, for this story, we take them to be flat. So,
but on S1, they are all flat, no?
sorry?
On S1, all G bundles are flat.
If G is finite, sorry. Well, no.
The mod is given by the monodromy.
That's correct if you put a connection on that. But if G is a continuous group, if G is a continuous
Hamilton, what corresponds to a Laplace, elliptic operator on the space here?
This I did not put an elliptic operator on this. This is going to be a topological field theory, so dynamics is trivial, meaning time evolution is trivial.
Or what is Hilbert space on which these operate?
The Hilbert space is a space of functions, class functions on G.
Okay.
That's a space.
And the scalar product is a natural scalar product you can.
Yes, if you want. And I should say that if we work in the topological field theory and the space are finite dimensional, then we can get away with algebra. So we usually don't start out by assuming as a Hilbert space structure on the vector space of states, just a vector space, because you don't have to do analysis, you don't need a norm, you don't need convergence. If you
what I don't understand is, for physics, you need some algebra of operators, which
Yes.
are observables. What are they here?
There will be operators on this space. They'll be coming up. So, but now I can only do half a page at a time, so I can't speed up quite so much. So let me just make one comment for a compact group, because that's what we'll focus on later. Clearly, you have a problem for closed surfaces because you can't just count bundles. There are ways to address that. For example, there's a compact manifold, G is compact, there's a compact manifold of flat G bundles on the surface. You can take its volume, you have to think how you normalize it, and so on. There are ways to address it. The rest is kind of self-evidently defined. But the space, in this case, is now infinite dimensions, and now you would want to put an inner product on it, coming from the measure. So there are ways to address the top dimension for semi-simple groups, and it's known as a topological limit of Yang-Mills theory in 2 dimensions. That was completely solved by Migdal, and Witten gave nice accounts of it. So I think it really was defined as a quantum field theory. So, all right. So now we're getting to address the question of what are the observables and the states.
So by that you meant just pure Yang-Mills?
It's really pure Yang-Mills, which is area dependent, and then if you set the area to 0, you get a topological limit that is slightly ill-defined. It's slightly infinite, but not hugely infinite somehow. So it still makes sense. So it's not a completely honest topological theory. It's regularized by that exponential Casimir coupled to the area of the surface.
Yes.
So, oops. Yes, that's it. So a general fact about this formalism of local theories is that the boundary conditions for a quantum field theory, topological quantum field theory, are the objects, the category associated to a point. In this case, a category of representation in this case. So I'm not going to explain it in general, but let's spell it out in this representation case how it works. So the representations of G. So let's spell out what this means, really. So what the story is, if you do away from the formal definitions, is it's a dictionary between a calculus of pictures, which are surfaces with corners, and the highly structured algebraic operations. Not that highly structured. If you stop at dimension 2, there are 3 layers of structure. As I said, algebras, bimodules, and intertriangles. So here's the first picture, is with to an interval. Gray is think of gray as a bulk, and anything colored is a boundary. So to an interval, on the bulk you have gauge theory, on the boundary you have 2 representations of G boundary condition. You should get a vector space, and the vector space is a space of G maps from U to V, U, V being 2 representations. So this calculus of pictures, to a closed manifold associated the vector space, to an open manifold, the manifold with boundary, if you color the boundary, it should behave just like a closed manifold. So you should get the vector space assigned to that. Here are some pictures that people always have been drawing for 30 years, I think, when talking about quantum TQFTs. So here we have 2 input circles. I guess I didn't draw it, but time goes this way. 2 input circle, 1 output circle. So this must correspond to an operation that takes 2 copies of A. So A should be black, I guess, to be consistent. The space associated to a circle from A tensor A to A. So that is like a multiplication of the space. And indeed, if you play a bit with pictures, you can show it's a theorem of, I should put the name here, so Lowell Abrams, I think.
Can I ask a question?
Yes.
This is like a topology change feature for us.
Yes.
So suppose I have a bundle on each of these circles initially,
Yes.
and I want to go to the file, but
Yes.
can I smoothly extend the bundle over intervening space?
Actually,
It's a cobordism problem, no?
In this case, you can because of the way it's done. But if I was closing, if there was no output, you would not be able to. So the operation is defined exactly as you say by counting bundles. So given the input bundles, look at all possible way to extend them to a bundle, and take the sum of a project that to the endpoint circle, and that gives you a matrix coefficients for these operations.
But is there always such a cobordism that you're writing on the bundles?
So in this case, if you think of the monodrome is yes, because what you have to choose if you have monodrome is a G and H on the inputs, and you put G times H on the output, that will work, for example. Because you just get a bare multiplication. But that's not the only way you can do it. G is not abelian. There are many other ways. There are other things you can do. Because G and H are defined only up to conjugation.
But suppose the initial surfaces are not circles, but some two, say S2, two S2s going into one S2.
Yes.
Then you have bundles with not trivial
then you finite gauge theory wouldn't give you a whole lot because you can't have monodromy on S2, but you would get something.
It should not be. It will be a U1 bundle. Not I don't want a flat bundle. Take an S2 with a U1 bundle on S2.
Yeah. So I mean, the answer is always so. Okay. So what's the procedure for computing it? That's a question. If I understand the question, the procedure for computing it is given by correspondence diagram. So I didn't leave enough space, but let me try it anyway since it's projected so large. You look at the modular. You look at all the bundles. Bun G on this surface, right? And this has restriction maps, the input bundles, bun G of S1 plus bun G of S1, and the restriction map to the output bundle. And the way we define the map is by matrix coefficients. Put a matrix coefficient on each of the inputs, each of the outputs, and count how many things are living above it here, and that's your matrix coefficient in matrices. Depending on the context, what you need to do is like pull back functions here and integrate them down. That would be the procedure. That's what the path integral does when there's a boundary. So anyway, Lowell Abrams proved that the structure you get in this setting is called the Frobenius algebra and spelled out exactly what that meant. Let me do something more interesting that includes now boundary conditions, because I mentioned those. So here I have a torus where I've cut out 2 holes, one as an input, one as an output. So this should be a map from A to A. And I cut out a 3rd hole somewhere in the middle. It's not obvious it's a hole, but that's what it is. And I put a boundary condition on it. So as far as what kind of operation I get, it's as if there was no hole here. It's a map from A to A. But what will matter is, well, when I compute it, I have to take into account that I've made a change here. And what happens again, you look at all possible extensions of bundles, input bundle, output bundle on the torus. But now when you sum them, you have to weigh the sum by the trace of the monodromy on the representation of V around the hole. And you might recognize it as a Wilson line in 2 dimensions. That's how Wilson line modifies the path integral or trace of monodromy on the closed lines. In 2 dimensions, the Wilson line has to be at the boundary, so there's not much else to do. More specifically, if you just take the cylinder, if you didn't do anything here, you didn't have the hole, as I said, it's topological field theory, so that would be the identity map. There'll be no propagation. But with a hole, that turns out to be convolution of the character of the representation. So BO0 reducible, that would be like a projection, a normalized projection. So in this story, there are 2 very distinguished boundary conditions. It's not unusual to meet them. There are the Dirichlet condition and the Neumann condition. And boundary conditions are representations, and specifically the Dirichlet condition is a regular representation of a group. The Neumann condition is a trivial representation of a one-dimensional trivial representation. So if you take the interval, putting a Dirichlet condition at one end and another representation at the other end, that's the underlying vector space of the representation V, because remember it is G-invariant homomorphism from the regular representation into V, and that just picks out the underlying vector space. If you take the Neumann condition and do the same thing, that's a trivial representation, you just pick out the invariant vectors in the representation. So I don't know if I quite convinced you of that, but the fact behind it is that the standard calculus of representations and characters for a finite group can be captured by TQFT pictures using cutting, composing, and sewing them together.
Sorry, in the previous picture you were coloring the boundary with V.
Mm-hmm.
So this would correspond to which kind of boundary condition?
V is a representation, right?
Right.
So,
yeah.
so
you just mentioned two type of boundary conditions.
yeah.
That of the picture on top is which one of these two?
Here it doesn't have to be. It could be any representation. Any representation gives a valid boundary condition.
So it's neither Dirichlet nor
V is not necessarily Dirichlet or no. Could be anything. So this is a correct statement, and this is a convolution. The character for any representation you could put 0, for example. Then of course the map you get will be 0. So that would be correct. So there is a. You don't want to rush it, but there is a little bit of practice required to correctly interpret the pictures and translate the calculus from pictures to algebras. So for example, you have to think to see what this picture means, where I have boundary conditions on some boundaries and not on others. It does mean something. And if you go in higher dimensions, it becomes slightly more awkward. But I hope at least I've drawn enough to explain that the TQFT, in this case for gauge theory and its boundary conditions, is the calculus of representations of a finite group, but encoded in pictures. All right, and then one more thing that.
So do your surfaces need to be compact?
Yeah. It's compact surface with boundaries or corners. That's right. Non-compact surfaces. I mean, just like in physics, if you didn't say what happens at infinity, you don't know what's going on. Seems to make sense. So now I think I'll just state more formally what I mentioned quickly early on. We know what full locality means in topological field theory. So this is work of starting with ideas of Kontsevich and work of Costello in dimension 2. Then Hopkins and Lurie made slightly more precise, and finally Lurie in arbitrary dimension. The theorem says that a fully local TQFT for framed manifolds, we can put that in parentheses for now, is determined by a single object in a D category that is assigned to a point, and everything is computable from that. But the object itself must satisfy some strong finiteness conditions, as we saw for the group, for example, the finite group. Now, in physics, we don't like frame theories. We like theories defined on oriented manifolds, or maybe on spin manifolds, or pin manifolds, or some kind of structure, but the framing is a very strong structure. And that requires a lot of extra work, which gets more difficult with dimension, but we know in printed theory, we know how to compute things. All right. So
The capital D was general in that last statement.
D was general, so yeah, that's right. It's no longer in dimension 2, so I think.
But do you really have usable pictures for Maya?
Well, we have, dimension 3 had actually been studied pretty well before the theorem by Turaev and Viro and by Rezhetik and Turaev. And there were good theorems in the semi-simple cases. And I don't think we actually know non-semi-simple examples now that really fit the assumptions of this theorem in higher dimension. Well, actually, no. Yeah, all the examples we know are in some sense semi-simple. So it's actually a good question if there are more sophisticated examples of TQFTs that are fully local and satisfy all the properties we want. If you abandon the condition that your vector space are finite dimensional, then we know how to produce lots of examples. But then if you stay topological, you have trouble with the numbers at the top, because without regularizing them, vector space don't have a dimension, even if dimensional. So you can't take a trace of the identity. But so based on this, you can now guess a general statement that would be correct, that representations of G on categories, so now we move from vector spaces to categories, so maybe I should write instead of vector spaces. Are boundary condition for pure three-dimensional gauge theory. And why is that interesting? Because now the boundary of a three-manifold is a two-manifold. So on the boundary you have now a two-dimensional theory that's coupled to a gauge theory, and we also know that as a gaugeable two-dimensional gauge theory. It's a two-dimensional theory with gauge symmetry. That's what you can put on the boundary of 3D gauge theory. So in a way, it's just a restatement. Classifying representations of G on categories with some finiteness conditions are the same as classifying two-dimensional gaugeable topological field theories. And some of the pictures I mentioned before apply universally. It takes too long, this procedure. There is, for gauge theory, a Dirichlet boundary condition and Neumann condition. And you build this slab or sandwich, or you put three-dimensional gauge theory in the bulk, the Dirichlet condition on one side and the gaugeable 2D theory on the other, you just get the underlying theory, forgetting the gauge symmetry. Whereas if you put the Neumann condition at the other end, you gauge the theory. So there's if you can execute this calculus, you can compute what you can know what the original theory was, you can compute the gauge theory. And this is now the correct way to think of higher representation theory of G, the algebra that governs gauge theory in higher dimension. All right, when we start thinking about it, there's first a mild surprise, which is that once you go to Lie groups, away from finite groups, there are several things can mean by representation theory, because correspondingly there will be several things you can mean by gauge theory in higher dimensions. And in 2 dimensions, I know of 2 of them, 2 ways of doing that. I call them the A-type and the B-type, inspired by the A and B models of mirror symmetry. And the B-type is what we've been talking about. The usual representations, linear representations of groups. That's what we mean. The A-type, we don't think of them as representations ordinarily, but you could call them topological representation. But G is forced to act just by its topology. So for example, you want to require that a contractible part neighborhood of the identity in G should act trivially. Now, if you take that too literally, that would force the action of the group to factor through its components. You forget the positive dimensional part, just remember the finite group of components. So that wouldn't be interesting. But there is a way to make it a bit more interesting if you let it act not just on vector spaces but on complexes. Then you can represent the full topology of G. And here's
only the homotopy groups of G.
Exactly, they can be represented, but you have to act on complex. If you act on a single vector space, you can just represent pi naught. So it's not interesting from that point of view. Well, it's not any more interesting than finite gauge. So here's the main example of such representation. If G acts on a topological space, then that space should have been a manifold, I guess, because no, manifold. Then it also acts on a Durand complex of the manifold, and that's an example of a complex. The easily visible part is that the group of components acts on the cohomology. The connected component itself is forced to act trivially, as the theorem in topology, so you don't see it. Nevertheless, there is a hidden data in the action. And if you ever computed a Lorentz spectral sequence, cohomology of a space from the Lorentz spectral sequence, you know that there are some differentials to work out, which can be quite difficult. If G acts on X, you can form a bundle over the classifying space with fiber X. And when you compute the cohomology of that, known as the equivariant cohomology of X, you have lots of Leray differentials to compute, and those encode the action of G, of the higher homotopy of G on X. So it's very hidden. It's in a sense, it's very hidden, but of limited interest for a homotopy theorist, because when G is connected, at least, it turns out the derived category of this topological representation is the same as the category of modules over the cohomology of BG, which is a polynomial ring, if G is connected. So it's, you're studying the modules over a polynomial ring, okay, we know we can do it, and it's not terribly exciting, and that's why I think we don't think of it as a representation theory of G in this sense. So what's surprising is if you go to 3 dimensions, it gets more interesting. But you have to look at all these ways of presenting G. So in 3 dimensions, I know, oops, I want to move this. I know 3 kinds of representations of G. I know 3 things I could think of as boundary condition for gauge theory. One of them I call well, let's start with the middle, the mixed AB type. I don't think it's a standard name, but there's a good reason to call it that. In this case, the gauge theory is Chern-Simons theory for a compact group G. And it has many nice features. It's fairly computable. It's nice semi-simple. It satisfies all the axioms of topological field theory. But usually it will have no topological boundary conditions, no non-zero topological boundary conditions. And if you want some analogy of representation theory lower down, you would say that maybe it has no finite dimensional representation, have groups with no finite dimensional representations. It does have a conformal boundary condition, the chiral WCW model, and that's maybe like an infinite dimensional representation. You want to think of it that way, it's not unreasonable. So this of course has been studied enormously, this example, so I will not say anything about it today. Let me just mention the maybe more obvious type of representation to define. I call it the B type by analogy with what happened here, just a regular notion here of a group action on a vector space. And here, there's an algebraic geometry analog. If G acts on an algebraic variety, it does act in the category of algebraic vector bundles, but also of coherent sheaves, and even a derived category of coherent sheaves. And that's called the 2-dimensional B model of X. And when you have G acting, you can talk about 2-dimensional gauge B model of X. That has been studied in algebraic geometry. You have algebraic varieties with reductive group action, or people are studying the equivariant derived categories and how they relate to the categories of quotients of G, and there's a vast literature on that.
So if you've got an algebraic variety, perhaps if it wasn't possessed of any singularities, it could also be of A type as well.
If it's Kähler or something, right? If you have a symplectic form.
Yeah.
Correct, yes.
So they're not disjoint.
No, but it'll be a different kind of thing. So yes, meaning from the same object you could build 2 different kinds of action, but there will be very different representations.
Yes.
They're not, in general, there's no relation between them. Mirror symmetry is supposed to interchange them, maybe.
Excuse me, sorry, are there any conditions in the representations? I mean, you say there's no finite dimensional reps for an AB type. I mean, a very trivial example is Lorenzo.
Well,
it's got no finite dimensional unity representation, but it does have finite dimensional representation.
That's correct, yes. Or even simpler SL2R, that's correct. I mean, the only finite dimensional unity representation is a trivial representation, but all the others are infinite dimensional. So that's the only analogy I could think of something which has no representations. But so I don't have any wisdom to offer about this. We simply know that a general Chern-Simons theory does not have topological boundary conditions. I think first people to point it out and have, maybe in the torus case, they had a proof of it with Kapustin and the Saulina, maybe. Actually, I wrote it in the wrong place. It goes with no topological representation, not with a chiral WZW. So I'm thinking of there is this maybe wish. I think I don't want to call it even a guiding principle that Now, if you have a quantum field theory and you go to the very low energy regime, one of two things happen. Either it's gapped and gives you a topological theory, or it's not gapped and gives you a conformal theory. So similar, so I'd like to say one of the two things happen. There's no theorem to that effect. I'm sure if anybody tried to formulate a theorem, somebody will come up with a counterexample the next day. But something similar you can hope happens with boundary conditions, that one or the other things happen. Either there's some conformal limit of a boundary condition or a topological limit of boundary condition. And what's curious is that there are examples where there are no topological boundary conditions. I don't know if there are examples where no conformal boundary conditions, no boundary conditions at all. I love to think that any quantum field theory allows some kind of boundary condition, but again, one can't state theorems of that kind and hope for them to be true. So let me finally get to what I actually want to discuss, which is the A-type representation. So it's a bad example, it's an easy example, that's why I'm starting with that. So when G acts on a topological space, there is a natural category on which it acts topologically, namely the category of local systems of X and complexes of local systems. So what's a derived local system? Maybe I should give a more concrete example so it's not so mysterious. Examples are in green. The example would be if Y to X is a fiber bundle, then the fiber-wise homology, a fiber-wise chain complex, so C star relative, C star vertical of Y to X is a derived local system. Of the same kind. If X is simply connected, for example, look at the homologies, then they form trivial bundles over X, but there's hidden information inside. And if G group acts on X, it will act on this coefficient system. That's an example of a topological action of G on a category as opposed to a vector space. And if you ask what's the two-dimensional quantum field theory that corresponds to it, we know the answer to that. It's what's called the string topology of X that was defined by Schass and Sullivan a long time ago. And it's an incompletely defined two-dimensional quantum field theory. The space of states is infinite dimensional. So in this case, the space associated with the circle would be the homology of the free loop space of X. Actually, that's true if X is a compact manifold, I should have stated. So if X is a compact manifold. So this gives an example of a boundary theory for topological three-dimensional gauge theory that fits the condition. It's not quite a finite topological boundary condition. It's a bit infinite. So the good examples are much more difficult to construct, which is they come from group actions on compact symplectic manifolds, Hamiltonian actions on that. And it is hoped that they give fully local TQFTs, but that's proved only in special cases. So to a point where they associate the Foucault category of the manifold, and hopefully that generates a quantum cohomology, the Gromov theory, and the whole story that much has been written about. So again, even independently of groups, that's not true in general, but you can hope that in favorable cases, when that is true, then a group action, Hamiltonian group action on X would give an example of such a topological representation, and this time on a quantum field theory that really is a finite topological quantum field theory, unlike this easy case where you get not quite finite things. So this is an example of finite dimensional topological categorical representation. So that's good, that's fine and good, but there's a surprise when we start studying that, which is that these actions admit a character calculus. And today, I think we recognize this as a first broad example of three-dimensional mirror symmetry. And let's me put the whole thing at once, if I can. Oops. So, first statement that been not completely checked, but partially checked, is that the three-dimensional n equals 4 supersymmetric twist gauge theory for G is equivalent to the Rosansky-Witten theory of a space that I'll introduce in a second, the total space for the Lagrange dual. Second, the character calculus of topological representations of G on two-dimensional field theories is captured by the holomorphic Lagrangian geometry of the set space. More precisely, two-dimensional gaugeable TQFTs give you coherent sheaves with Lagrangian support in this space. And the underlying field theories and gauge field theories are computable by intersecting with some special boundary conditions, the Dirichlet Lagrangian, the Neumann Lagrangian inside. And one slogan that goes to this is that the two-dimensional mirror symmetry is recovered at the boundary of three-dimensional mirror symmetry for G. And I won't make that slogan precise, but I'll now work out some examples from something relatively easy to oops, why did this happen? Okay. Something relatively easy to something more sophisticated. All right, so let's start with the torus case. The abelian case is always easier. So in this case, what I call the total space for the dual torus is just the cotangent bundle of the complexified dual torus that projects the cotangent fiber. It's a product, of course, projects the cotangent fiber, and this projection is an holomorphic integrable system. There's a symplectic structure, the Lagrangian fibers, and it's even a fiber-wise the group over the base. The base is the Lie algebra of the original torus, and functions on it are the equivariant cohomology, the cohomology of B of the torus. So that's going to be the setup in general. So total space for G check will map to this spec, meaning the space on which the functions are the equivariant cohomology of G. So and it will be an integrable system. That will be true in general. And it turns out this case, at first sight, is governed by standard spectral theory. At least in the abelian case, you might expect one-dimensional representation to tell you everything. And indeed, one-dimensional representations of T correspond to points in the dual torus. I mean, that's a basic enough fact that I try to explain it. It's kind of important. I mean, it shouldn't be surprising. Abelian groups, if you know the one-dimensional representation, you should know everything. So let's see what that means. So the group itself can be written as the Lie algebra modulo a lattice, pi1. And for a topological representation, because the Lie algebra is contractible, the vector space, saying that you have a topological representation is saying that you've made the action of the Lie algebra trivial. That's a requirement. But now, the pi action was already trivial because pi maps to the identity in T. So what you've done is on pi, you have two different ways of making the action trivial. Now, if you're acting on a vector space, trivializing the action twice would be either a waste of time or work for extra credit on the exam because you're not learning anything new. But when you're acting on a category, making something equal to 0 or 1 twice is giving you something because you don't have equalities in the category, you have isomorphism. So you're saying x is isomorphic to y, and again x is isomorphic to y, go around to get an automorphism of x. So the information here is an action of pi as automorphism of the identity function to the identity map from back to itself, and that's just a homomorphism from pi to C star, and that's exactly a point in the dual torus. So that's a spectral categorical spectral theory for a torus. It's not very exciting, but thankfully that's not the end of the story, and that's because we have physicists to tell us where we went wrong. So topologists like things to be Z-graded. You have homology or homotopy that's graded by integers. But physics is usually Z2 graded. Spin statistics. Now, in this space I introduced, the cohomology of B of the torus is generated in degree 2, this space is graded, has degree 2. So if you insist on Z homogeneity, everything you build has to be conical, the cotangent bundle, and then basically you know it if you know what happens near the zero section. So in fact, the space kind of becomes useless. I mean, if the fiber is being graded and insisting on homogeneity, it's kind of telling you that you really want to look just at the torus, and that's what we're doing here. But while that's true, I mean, if you ask instead for Z2 grade objects, well, the grading was even, so mod 2, there's no grading whatsoever, which means there's no reason to look at conical sets. You can look at any subsets in here. And in fact, what we're going to see Lagrangians in the cotangent bundle of P check that are not necessarily conical. They're only possible if you abandon, if you collapse the grading mod 2, or I guess at least mods are even numbered. So in this case, the Lagrangian going with the point in the torus would have been the cotangent fiber at that point. That would have been the correct interpretation of that one-dimensional representation. And now here's an example. It's a real-world example where we actually see that. So how much do I need to start with this? Real-world example is, it's probably the only example I can compute in Floer theory. That's not my strength. Is the equivariant mirror of P1 equivariant for the rotation action, circular rotation action. So in this case, a group that acts as a U1 is dual, is also canonically U1. And the total space, as I said in gray here, is a cotangent bundle of the dual torus. We have a zero section here, the cotangent bundle, which I call the Neumann condition, and the fiber at 1, which I call the Dirichlet condition. And there's a projection I mentioned before, just the Lie algebra of the torus. That's a Toda projection. The fibers are tori. That makes an integral system. There's also a projection to the dual torus in this case, which gives you a coordinate z. So I have two coordinates, maybe tau and z in the space. And in orange here, I've drawn the graph of a function. The function depends on a parameter q that you fix, and it's given by tau is q times essentially sine of log z, z minus z inverse, and that's the differential of a function. And the function q times z plus z inverse, you might have seen it as the standard superpotential for the mirror of P1. If you open a book of mirror symmetry, probably the first example done is that tells you that the mirror of P1 is a torus C star, complex torus C star, with a superpotential given by this formula. And Q is a parameter for quantum cohomology. And as you see, it's not conical, right? It's only possible because in quantum cohomology, the grading has been collapsed. I think in this case, mod 4 doesn't need to collapse. You don't have to collapse mod 2. So what's the meaning of the picture? Well, the functions on the graph turned out to form the equivariant quantum cohomology of P1, E1 equivariant. The usual way you see it presented in most books is take a polynomial, well, Q, I guess, the polynomial ring over Z in two generators centered at 0 and infinity with a relation. And classically, you would write omega 0, omega infinity is 0. That would be the classical equivariant cohomology of P1. And these two come from the fixed points at 0 and infinity. The quantum deformation puts us q squared where you had 0, and the relation to the variables before is tau is a difference, the variables, and z is related to omega 0, O, and there's probably an inverse there. Infinity inverse, I think. Yeah, the product has to be q squared. So that's a picture of the representation of topological representation of U1 on the Foucault category, Foucault-Floer category of P1. What can I point out more? I called some things Dirichlet and Neumann. So let's explain why I called them Dirichlet and Neumann. Well, what's the intersection with the Neumann line? Well, you see 2 points here and there. And That's just setting tau equals 0. Tau is a coordinate in this direction. So tau equals 0 is the Riemann line. And what you get when you set tau equals 0 is you can abandon omega infinity as a generator. So you get Q of one generator whose square is Q squared. That's the ordinary quantum homology of P1. Intersection of a Dirichlet line at z equals 1. Just that will be this vertical line. So you get a single point now. So you just get the algebra Q. And Q is indeed the answer for a U1 gauge quantum cohomology for P1. And it equals, these statements are trivial, it equals the quantum cohomology of P1 symplectically reduced by U1, because that's a point after all. But this trivial calculation is just a special case of the Batire formula for quotienting toric Van orbifors, just for P1. Okay, so let me draw the general case, because it gets a little more interesting, the non-abelian case. Well, general case, I guess, will be SU2 and SO3. That's what I draw. So a Toda space for a non-abelian group is closely related to the one for a torus. We more or less start with the one for a torus, divide by the Weyl group, that creates some singularities, and there's a very specific way to resolve them, to get a holomorphic symplectic manifold, by blowing up. In the case of when the group is SO3, we just create one singular point here, which have a quadratic singularity, which you have to blow up once to get an exceptional divisor, and then in the affine space, we remove the zero section. If we left this in, this would not be an affine space, and it's important for the story that the space is determined by its basis function. In this space, once you do that, what used to be that parabola-looking thing, it's not a parabola, here, becomes a Lagrangian that curves around and intersects the zero fiber twice. And that is the SU2 equivariant quantum cohomology of P1. In this case, the ambient space is the known as the Atiyah-Hitchin manifold. It's a hyperkähler manifold. All the Toda space are hyperkähler manifold. There is here I looked at the equivariant cohomology for SU2. Of course, the action factor is through SO3, and then you could do a little game of switching to the group is SO3 here, in which case you're looking at the Toda space for SU2, and that's a double cover of the Atiyah-Hitchin space, and now the former parabola looks a bit more like it was looking before. All right, here's a general theorem. So first part is that the Toda space for any group, Langland's dual of a group, has a holomorphic Lagrangian foliation. In this case, if you vary the parameter Q, you'll get a complete foliation of this space, just two exceptional leaves here. And the leaves correspond to all the flag varieties of G with their small quantum parameters. And the bulk of it is an open dense set that goes to the full flag variety. And that's what Toda originally defined as a phase space. So the improvement by adding the boundary strata came later. And this, of course, this result has a long history, given Tan and Kim 25 or so years ago. They did part of the story by projecting they looked at the projection to the Toda base and used that to describe the quantum cohomology of flag varieties. They never drew the picture of the Lagrangian inside. They had the space, they knew it was the Toda space and projected. But somehow the Lagrangian picture was not there. The other projection, I see I forgot to put that in. Again, it wasn't written, but it's implicit in Zeidel's work. It's a projection to the other projection to dual torus mod divide. That's a projection to this side. So somehow both halves were known but not put together. Then maybe a decade and a half ago, improve the results of Giventhal Kim and several other people I didn't mention, and she constructed B-model mirrors of the flag variety. And then one of the things I checked when coming up with that is that her mirror, the mirror she proposed, we spelled reach, I think. I think it's this. That her B-model mirrors were equivalent with the ones I constructed from the foliation. The foliation is defined differently. I'm not going to tell you how, but there's a notion of, maybe I put the words here, mirror equivalence. Where you can check that the leaves you get naturally really give the rich mirrors of flag varieties. So somehow the calculus of representation is given not by points in this space, not standard spectral theory, but by Lagrangians. So you don't have things like irreducible representations with Schur's lemma or a home between distinct irreducibles is zero. You can't have that because two distinct Lagrangians can intersect. But there seems to be a preferred foliation, which is like a complete exhaustion by irreducibles, and the irreducibles are built from flag varieties, but symplectically, not by like holomorphic induction, but by some kind of symplectic induction. And the second part of the theorem, which depending what you want from it, it's a theorem or partly a conjecture, so partly a conjecture, is that two-dimensional gauge theory with G gauge symmetry, two-dimensional, sorry, that's a mistake, not gauge theories, two-dimensional TQFTs. TQFTs with G gauge symmetry, not gauge theories, lead to coherent sheaves with Lagrangian support. What happened to this? What else? In the total space, so that intersecting with the Dirichlet boundary is a space of states of the original theory. Intersection with the Neumann Lagrangian is a state space for the gauge theory. And I have to say it's a conjecture that intersection of the leaves of the foliation computes the following picture. Take the three-dimensional gauge theory bulk, put a boundary condition from the flag variety and your favorite gaugeable TQFT on the other side, project down to get a two-dimensional TQFT, and that's what you should compute. And why is this a conjecture? Because I don't think it's proved yet that all A models of flag varieties give fully local TQFT. So the Kontsevich-Fukaya program is not quite proved. It's believed to be true for flag varieties. Okay, I'm almost, well, actually, I'm at the end of my time. I just have one page of applications, very quick page. The first application is really a sanity check, namely looking at gauge theory for a point, right? So you want pure two-dimensional gauge theory should arise by gauging, right, the trivial two-dimensional boundary condition. Well, when Witten redid two-dimensional Young-Mills theory, he gave a topological interpretation for that in terms of a class, maybe I should have put it here. So class tau naturally lives in H4 of BG. So, and he interpreted his theory as in terms of integrating a symplectic form on the moduli space of G bundles. And the symplectic form was built from a class in H4 of BG. Tau squared. So you want to see, in that case, he showed that the two-dimensional gauge theory was semi-simple, and it had a basis that could be put in bijection with the irreducible representation of the group. So in the abelian case, it would be just integer points in the Lie algebra, integer lattice points. And in the non-abelian case, Weil orbits of regular integral characters. So when you run through the machine telling you what Lagrangian you should write for the trivial boundary condition but deformed by this class in H4, you find that the Lagrangian is the exponentiate graph of a differential of a superpotential which is just built from the homology class. So when you spell out what that means in the abelian case, the differential of this is 2ht. Exponentiate that, the Lagrangian comes from the equation z is e to the 2ht, and these are the leaves because this is the z direction vertically. This is tau on the base now. Because of this is a z a periodic direction, this wraps around, comes back to intersect the zero section of many points. In the non-abelian case, the total space gets a blow up at the origin. Now, when you blow it up at the origin, because this line doesn't come in tangent to the red axis, it fails to intersect the origin, so you lose the point corresponding to 0. So the orbits you get are just the regular integral coadjoint orbits, and you lose this one. So that's simply a feature of the blowing up in the geometry of a total space. So you can identify the algebra computed from this picture, from the intersection of the orange Lagrange and the Dirichlet condition, with Witten's two-dimensional topological Yang-Mills theory. Of course, if that failed, the theory had to be wrong, right? So that was the first check. The slightly more interesting check is the penultimate example, I think. Is what I call the quantum GIT conjecture. That's now partially proven, joined with my former student, collaborator now Dan Pomerleano, which says that for a compact Fano manifolds, the quantum cohomology of the GIT quotient is the same as the gauged quantum cohomology, which is explicitly computed by a Lagrangian calculus I discussed earlier, intersecting with the Dirichlet condition. So there's an explicit formula for this in terms of that, the conjecture. So it proved part of it. Actually, we proved that this statement is true, we just don't have a very nice, we're not sure we have a very nice map that relates one side to the other. It's a guess about what the map is. That's highly non-trivial. And in fact, I tried very hard to find proofs using algebraic geometry, which I know a bit, and the only arguments I know use is Floer theory in a pretty heavy way. And the third example, I'll just mention the words. There's been a lot of interest in Coulomb branches for 3D gauge theory with adding linear matter, quaternionic representation. And the linear matter is, of course, an example of an A model for G, just happens to be linear, so it gives an explicit Lagrangian you can compute. And that is enough to determine the Coulomb branches for gauge theory. So you can say it in many ways, but one of them is the minimal way to extend the original total space and makes it compatible with charge conjugation, the conjugation that switches the two representations V and V check. On the original space, that charge conjugation would have singularities within some things to infinity. If you complete the space in a minimal way to fix it, you get what's called the Coulomb branch. So I was very happy to see that, but it's actually a disappointing result in some way because it tells you that the Coulomb branch for three-dimensional gauge theory is formally a consequence of the two-dimensional linear sigma model. So whatever we learn from Coulomb branches, we could have learned by looking more carefully at the two-dimensional linear sigma model, which is fairly explicit. But that doesn't mean we're not going to learn something new. And I think that's all I have.
Okay, thank you very much. Questions?
I can ask you a question. I want to place it in a physics context.
Right.
So the way I see these models, the topological field theory as it stands, I don't know how to use it in physics. But I can see such things happening if you have, say, a circle initially, and I write the Dirac operator minus I d, and the boundary condition you are giving is defining the domain of that operator.
Defining the?
Defining the domain of that operator on a Hilbert space. Yes? Because the holonomy is a circle.
In that example I'm thinking of, I would think boundary conditions are meant to be looking at the Dirac operator on manifold with boundary and specifying something at the boundary. That's how I would interpret the boundary condition. You want to think that the circle itself is the boundary? That's
No,
what I interpret.
any point of the boundary, the holonomy, if you go around to that point. So if you don't like that, you can make it into a three bond. That's fine. Okay? So the boundary will be the boundary of the three bond.
Okay.
That's also fine, but it's more complicated. Okay?
All right.
But if it's a circle, the boundary will be any point you choose on the circle. So when the Dirac operator, when you do the Feynman analysis,
Yes.
the domain of the operator can change by a phase as you go around.
Okay.
Finally, you choose a different phase as you go around. So the domain of the operator has changed from initial to final. So and you can imagine time evolution as given by this exponential of this Dirac operator along that mapping cylinder you are writing. Okay? But the problem is, because the domain is going on changing, one doesn't know how to write this exponential. And there is some analysis. In fact, we had argued about it last time I was here. Because you can't exponential IT times operator, you can't multiply it from two different times. So there is a formula due to Trotter, which is much more complicated to do that. So if I now do this and rub off the operator, I get these pictures. So it seems to me what is done here is mapping domains to domains of some elliptic operator which is of physical interest. It seems to me. I will interpret it that to use it.
You could sort of put that, use that as an input in some honest physics theory.
Yeah, that's what I'm asking.
It would classify some kind of connected components of a parameter space of the theory.
So here's my.
Yeah.
So if I can think like that, then it is not very clear that there is any smooth evolution of this domain as you go from the initial to the final thing. Okay? Because the domain is going on changing, and in the final case you have a different domain because of this functor, the mapping you're right.
Yeah.
Now, in general, what happens if I do a index theory analysis for so take a board, okay, B3, let's say, okay, and you have two spheres as a boundary, and you take the Laplacian in the then the analysis we heard many people have done is that the deficiency indices or the deficiency subspaces are infinite dimensional. So the unitary operator integrating them is infinite dimensional. It's not finite like this, but it is unitary. Yeah. And often you want it to be trace class. But anyway, that is how does this analysis adapt there? This unitary operator will change from initial to final in this kind of model.
So I mean, I think I don't think I'll be able to answer your question, but I can, as I said at the beginning explicitly, the premise of the story is we're taking out the analysis and focusing on the algebra, because the surprise was that the algebra is already complicated enough, and I hope I convinced you of that. Because you might even the abelian case, you might think, oh, we understand, just take the definitions carefully, you understand what it means for a torus to act on a category. And then you find out actually it's not, because mirror symmetry for toric varieties, for example, is a special case of that. It's already complicated enough. The place where I see this helping, just talking to physics colleagues in honest quantum field theories, is that there are what I call extended symmetry, extended operators in quantum field theory that are not just supported at points, but on submanifolds of space. And some of them can be topological, and they can give you constraints on the physics. And so it's a bit like having TQFTs embedded inside your honest, bigger quantum field theory. That's roughly how it works. And that's where I think the algebra of knowing how to handle those symmetries is useful. I don't immediately know how to...
You're referring to what is called non-invertible?
Yes, that's what they call it. Yes, I don't like that term, but yes, I mean, that is what... they're right. I mean, it's true. But I think there were non-invertible symmetries before, but and these are somewhat... The extended operators may be better. I don't know how to say that. I would be lying if I said I know now how to take this story of gauge symmetries, TQFTs, and now put an honest QFT instead. I mean, that's not even close to something.
These are monoidal categories.
Yes, sir.
These categories you're talking about.
The target category has to be monoidal always. That's yes, sir.
Is it also Hopf? There Hopf structure also?
Not
or R matrix.
well,
Yang
the R matrix
matrix
comes in as represented on things we build in the category, but target categories all require symmetric monoidal. But normally it's something which starts with numbers at the top, vector space below, maybe linear categories or algebra somewhere below that, and then it becomes sometimes, if you want to stay semi-simple, you would use finite tensor categories, fusion categories below, and after that it's not completely settled what we should take for the finite picture. For honest quantum field theory, surely you need something a little more sophisticated than that. We don't know how to do it. I don't know how to say that an honest quantum field theory is completely local. I don't know how to do the calculus of cutting with corners.
We want to discuss things like exchanges of two of these things, tensor product. Then one would like some R matrix to do that.
Right.
That's why I was asking.
Yeah, those, I mean, so you can, there are many pictures to realize that. For example, it's exactly like braids inside some, embedded inside some, these are topological defects embedded in some bigger manifold. So that's one, that captures that kind of question. Maybe in simple example, we might even allow it some dependence on metric or something easy. I think the difficulty, the place where things that I know break down is once you want to cut space-time with corners or higher codimension corners, we just don't know how to graft sort of analytically the spaces together. So that's the big mystery. But that's all.
Can I ask, how is this picture connected to the standard picture, a functorial QFT picture for 2D digitals? So where you assign the Hilbert space to a circle and then order them to assign like an operator. You see example of that like backwards on.
Or was that somewhere? Yes. So here, right?
Yeah, so I see you got the same thing in the end,
Yeah.
but it's like the category started where your objects are points rather than your objects being n-1-dimensional manifolds.
No, objects are points. So it's as you go higher in codimension, you have to increase the categorical level because every additional dimension is an extra layer of composition laws. So you can think of them as algebras with many multiplications. First, they may start being just vector space, but if you want to build up from there, you have one multiplication, a second multiplication on top of that, and that continues.
But isn't the normal picture of a d-dimensional gauge theory where you assign like space of states to a d-dimensional manifold?
Okay, all right.
Right.
It's maybe a d versus d minus 1, but aside from that, that's correct. There's a space assigned to the circle. In this two-dimensional, there's a space assigned to the circle. In my labeling, D is a dimension of space-time, not of space. That's all. That's the labeling thing. And yes, so for the top, for surface, you get numbers if they're closed. If they're not closed, you get operations. Spaces. That's enough.
Any other questions? If not, Constantin is around for the week, so let's.
Yeah, I'll be happy to
again
share my little wisdom.
Okay. Session. One question.
Ask John why exactly you have to use like the language of
Because when you ask